I'll just let him talk. We've got the recording going. And if you have any questions in the room, please, before asking, let me bring you the mic so that people online can hear, okay? All right, go ahead.
All right, thank you so much. Well, I want to thank the organizers, both local and remote, for the opportunity to present our work. The papers that I'm going to talk about are led by people in our group called Symmetry Group. So the talk is mostly about symmetries, but there are other topics, as Colin mentioned, that our group is interested in and we work on. So let's see. All right. So to begin with, probably many of the audience of this series is familiar with symmetries, but I'm going to start from the beginning. The way we define symmetries is by defining a set of transformations that keep an object invariant. So we have the set calligraphic T, including a bunch of transformations that do not change the object X. And these transformations obviously compose with each other, because if two transformations do not change an object, their composition also leaves that object invariant. And this compositional structure of these transformations is given by a symmetry group, G. Now, this becomes more clear as we go on. A group G is a set with a binary operation, and you can think of this binary operation as being corresponding to the compositional structure composition of these transformations. And it has some additional properties. So to make this more concrete, we can think about transformations as actions of abstract groups on sets. We have this transformation T that takes an element from the set X, takes an element of the group, and produces another element from the set. In this case, the teapot is being rotated, so we have a rotation group. And the group is the abstract group of rotation, and it's acting by rotating the teapot along the z-axis. It could have acted differently. It could have rotated the teapot along the y-axis or rotated the lighting of the room instead, which means that the same group can act differently even on a single set. So here, what we mean by the fact that the compositional structure of the transformation T is given by the group is that if we compose these transformations corresponding to G1 and G2, it corresponds to a transformation that's given by the composition of these group elements. Okay, so far we know what a group is and how it acts on a set of objects. Special type of action that is very well studied and is quite relevant for the design of invariant and equivariant networks is the linear action of a group, which means that this transformation is actually can be written as this matrix multiplication. So for each element of the group, we have this invertible matrix rho that we call it's a representation of this group. So when talking about symmetries or groups, we usually talk about either finite groups that correspond to discrete symmetries, like set of all permutations of n objects, or cyclic translations, or we talk about continuous symmetries, which are represented by Lie groups, such as continuous 3D rotations. And to give an example of representations corresponding to these abstract groups, you can think about an n by n permutation matrix being a representation of a permutation group. But there are other representations corresponding to the same group. It just tells us how the group is acting on that environment, on that set. And as an example of a representation for SO3 for continuous rotations, we have the rotation matrices, for example. So with that, now we can define what invariance and equivariance is. Invariance enables us to bring the notion of symmetry to the space of functions. So we have a function f, we call it invariant, if transforming its input using these group representations or group actions does not change the value of the function. For example, if we have a function that's predicting property of the molecule, we want it to be invariant to the rotations of the 3D rotations of the molecule. Equivariance instead is more general. It says that if we transform the input of the function, the output is going to be transformed, potentially using a different action of the same group. For example, if we have this molecule and we're predicting force fields, so predicting a vector per each atom here, if we rotate the molecule, we want these set of vectors that we're predicting to also be rotated. And this is usually visualized using these commutative diagrams. So you have the input x, you are transforming it and then feeding it to the function, or you first feed it to the function and then transform the result, and you want these two to agree, meaning that you want the diagram to commute. So now that you know what equivariance is, I'm just going to skip the whole part that talks about equivariant networks, because we are going to talk about the problems with equivariant networks. So over the years has been a lot of work, including some by our group, trying to design equivariant networks. These usually involve making individual layers in a deep network equivariant, but there are some problems. I'm going to point out what these problems, these shortcomings of equivariant networks are, and then I'll talk about a bunch of different works where some of these problems are being addressed in each of them. So one is that a lot of times the symmetries of the domain are inexact. And so an equivariant network is sort of over constraining the task. If, for example, we are using a covenant on text data or even on images, sometimes the assumption of having translation symmetry is not really exactly correct, depending on the task. Sometimes the problem is infeasibility. As I said, equivariant networks assume that the input is transformed using a linear transformation, because we can only design equivariant networks for these linear representations, linear actions of the groups. In general, if you have a nonlinear action of a group, or if you don't know what transformation has been applied at the input level, you can't design equivariant networks, or you couldn't. Another problem is that they cannot break the symmetry of their inputs. One major problem is the computational cost. So for certain equivariant networks, especially if you're dealing with high order tensors, for example, in modeling equivariance to rotation or higher order interactions of bodies, you get these layers that are quite expensive computationally. And this computational cost has a trade-off with expressivity. So you can have a more computationally expensive model to get more expressivity, but if you cut on computation, you're going to also lose the expressivity of your model. And finally, there is an overhead for the end users because they just want to use the equivariant network. They don't want to get involved with so many details in creating them. So what I'm going to do is that now I'm going to just go very quickly over a bunch of works that try to address one or more of these problems with equivariant networks. And they don't involve equivariant networks, but they try to use symmetries in those particular tasks. So the first one is tries to reduce the cost of equivariant networks using canonicalization. So these include two works presented at ICML and NeurIPS. So equivariant networks can be expensive. What can we do about it? So here's the idea. You can build an equivariant network out of a non-equivariant network by doing the following. Whatever input, so this f function is not equivariant, it's unconstrained. But whatever input I give you, you put it in a canonical form. This function h produces a representation, meaning that it is transforming x to a canonical form. You feed that to a constrained network, and you take the output of the network and transform it back. So you see that we have h inverse here and h here. So what is gained here is that because these canonicalization networks, h can be really lightweight, they can be very simple networks, you can get equivariance for much cheaper than what you usually get using equivariant networks. So, and another sort of benefit of this approach is that you get universality of the equivariant network simply by having universality for the unconstrained network. That is, you don't need expressivity for h. H could be as dumb as you like. So here's an example. Suppose you want to predict a vector quantity for your molecule, but you have rotations of the molecule, right? So you can take these molecules, and the canonicalization function is going to put it in a canonical form. You do your prediction using an unconstrained network, and then you can transform this vector back using the inverse of this canonicalization function. And we show that this could be computationally more efficient than using equivariant networks. This is comparing to group convolution for image task. We see that as we increase the order of rotation in our equivariant networks, the group convolution cost grows, but it remains pretty much the same for canonicalization. But a very important benefit of this approach is that you can apply this to very large pre-trained models. So you basically don't touch the pre-trained model, you just train a canonicalization network to canonicalize its input. So here's an example. This is the first row, is the mask generated for images. This is a ground truth mask. It's actually the mask generated by segment anything network, where the image was fed to this network in its usual orientation, normal orientation. But then if you rotated that image and fed it to segment anything, it would screw things up. If you add a canonicalization and learn a canonicalization, basically, then you can get pretty much similar quality as the original network, with a very marginal increase in the number of parameters and the inference time. So you get to make your pre-training models equivariant at a low cost. Okay, so that was the first work. There is a raised hand, I see. So yeah, please go ahead.
So for the canonicalized equation, you have h of x and h of x inverse. Does this assume that your domain and codomain are the same then?
Does this assume what? Can you say that again?
Does this equation assume that your domain and codomain are the same? Because h of x inverse seems like...
So the way you actually do this in practice is that h is gonna output an element of the group, for example, a rotation matrix, right? And then this rotation matrix is used to transform x. And both h and f are trained end to end. That is, you're learning to canonicalize to make the life easy for your unconstrained prediction network. And that makes a big difference. But once you have predicted the h, then you also directly have access to its inverse. You don't need to calculate that again at the output level.
Right. But if you're doing a rotation matrix, then that assumes that you can also rotate the output with that rotation matrix, right?
That's
so
right. Yes.
They both have to be vectors then.
They both have to be, oh, you're saying that
Vectors.
they need to be the same representation. That was the question. Okay, now I understand what you
Yes.
asked.
Yes.
Yes, you need to be able to convert between them. So if one of them, basically, if one of them has more information than the other, you can just predict that one and get the second one, derive the second one from the first. But in our applications, they've been the same.
All right. Thank you.
And if I can complement this answer, you can make it more general by having this canonicalization network output an abstract group element, and then you can use the representation you want on this abstract group element. So there is actually no real constraint in terms of domain and group action, basically.
Good. Yes. Great. So this is Omar. Omar led this project. Thanks, Omar. So now I'm going to quickly do a slide discussion of this other work, which is about regularizing deep networks using symmetries. So the problem that's being addressed is not computation anymore. This is about infeasibility of designing equivariant networks where we don't know the group, or sometimes maybe you even know the group, but the symmetries are not exact. So you don't want to constrain the model directly. What you could do is the following. So you can use the knowledge that if you have a finite symmetry, then that leads to weight sharing in the corresponding equivariant network. So you could directly regularize the model to have weight sharing, meaning that whatever your original training loss was, you just add this regularization penalty, the same as that you do for sparsity. But here you're encouraging the weights of your network to be the same. And you have L1 regularization, meaning that you want to have exact sharing. So this idea has been in the air. This project was led by Mehran, and what he was able to do was to come up with efficient and GPU-friendly algorithms for this. And for the first time here, we were able to actually apply this to networks with tens of millions of parameters. So what you see here is Gabor filters that Gabor-like filters that you learn if you use this kind of weight sharing regularization in an MLP, which you see these filters are also being moved around, but they're not exactly identical, which might refer to the fact that the symmetries are not really exact in this data set. Okay, the next work is led by Omar. It's on symmetry breaking. So I have one slide around this. We know that equivariant functions cannot break the symmetry. This is a problem. So it means that if you have an equivariant network, you cannot map a more symmetric input to a less symmetric input. Okay, so why is this a problem? Suppose that you have a bunch of items and you want to assign them to people. So you have a task that involves mapping a multiset to a set. So here, if you want equivariant to permutation, meaning that permutation of inputs should give you permutation of the output, so that you have proper assignment, this function actually cannot be equivariant, because here, if you swap the two donuts, then the output should also swap, right? But the input hasn't changed. How could the output swap? So this basically is pointing out to a problem with the definition of equivariance, in a sense that it doesn't account for the fact that you could have symmetries in the input. So what we did in this work was to propose a relaxed notion of equivariance that basically says, as you transform the input, the output should transform, but up to symmetries of the input. So in this case, if you now swap the donuts, because these are symmetries of the input, the output can remain the same. There are also some headway towards designing relaxed equivariant networks in this paper, but I don't think the problem's settled. There are a bunch of interesting follow-up works, including one from Omar that is in my list. All right. The next work that I'm going to talk about is led by Tara. This is about using symmetries in solving differential equations. So there are basically methods for solving differential equations using deep models. And here we wanted to use symmetries in this context. Again, equivariant networks are going to be problematic. So let's see how. So first, I need to introduce to you a family of neural solvers that are called physics-informed networks. The idea is that, so these are very popular networks for solving differential equations using deep models. And then the reason is that they don't need any sort of training data. So you don't need to have ground truth solution to train your model. The way they work is the following. So I'm going to show you through an example. Suppose your equation is a simple harmonic oscillator. This is the equation for the harmonic oscillator. And you want to find the solution theta for given initial boundary conditions. So what you do is that you use this neural network theta of x to represent the solution. You can use automatic differentiation to get the derivatives that appear in the differential equation and set your loss function to be the differential equation, basically, meaning that the loss is going to be positive if the equation does not satisfy, if your network does not satisfy the equation. And the loss will be zero if the equation actually is satisfied. And then you can have additional losses to just enforce initial and boundary conditions. So if you try to now optimize this loss, you will get a solution to the differential equation. The way symmetries come in is that with differential equation, symmetries transform solutions of a differential equation to another solution. So let's see again through this example. So if you have this simple harmonic oscillator, if you have a transformation of the independent variable x using T1, you have a transformation of the dependent variable theta using another symmetry T2, and there will be an implied transformation of the derivative using this implied transformation function T3. Now, if this transformed versions of dependent, independent variable, and derivatives still satisfy the equation, it means these are the symmetries of the differential equation. For example, in the case of harmonic oscillator, you can generate all the solutions through these symmetry transformations, but this is not generally the case. Still, a good span of symmetries could be covered by through these symmetry transformations. So, okay, so now how do we do this? How do we use symmetries in physics-informed networks? Well, one thing is that first we have access to these symmetries. If you hand me a differential equation, there are mechanical ways, there are actually packages that derive the symmetries for you. So you have the symmetry, you want to be able to solve these equations fast, or you want to be able to, numeric or using deep models, get the solutions fast. Can you use them? Well, the first idea is to use equivariant networks, but they're not feasible because the actions of these symmetries are often nonlinear. So in the case of a harmonic oscillator that I showed you, I believe only one or two of the symmetries out of the 8-dimensional space of Lie groups, Lie group corresponding to the symmetries of that equation, only 2 of them are linear. The rest are nonlinear. And also these symmetries are different for every differential equation. And so you need to, even if they were linear, you would need to design just a different equivariant network for each case. So our idea was the following. It said instead of using an equivariant network, we can use a loss function to inform the network about these symmetries. What the loss does, it says that because these are continuous symmetries, it says that infinitesimal symmetry transformations around one solution should land you in another solution, right? So it should be orthogonal to the gradient of the PDE loss, meaning that if the loss was 0, you were at a solution. If you do a symmetry transformation, you should stay at a solution. If you just use this loss in addition to your usual loss in physics-informed networks, we show that in some applications you can get much better sample efficiency. This is showing, for example, the heat equation. This is the ground truth for a given initial condition. If you don't use the symmetries using a certain number of samples from the domain, this is the solution that you get. If you use symmetries, you get a better solution. All right, I'm going to just keep going. So the next work I'm going to talk about is the application of symmetries in self-supervised learning. So actually symmetry transformations come in, they already come in and they're already being used to train self-supervised learning models. The way they're used is that in models like SimCLR, for example, in methods like SimCLR, you transform the input and you have loss functions that encourage the representation to stay the same. So you have these transformations of the dog and you say, I want representations for these different versions of the dog to stay the same. But this is actually not good because it's discarding information about the transformation. The representation is invariant to these transformations. Ideally, we want representations that are equivariant to these transformations. Our main sort of deriving application is in reinforcement learning, when you can think of the action of the agent as creating transformations of the data, and you want the representation that you create to be informed about these transformations. Okay, so how do we do this? Can we use equivariant networks? Again, it is kind of infeasible because, well, first, some of these transformations are nonlinear. And even if you just considered linear transformations, you need to create a network that is simultaneously equivariant to all of these transformations, which is kind of a challenge. So what can we do? So we want to create self-supervised learning methods that preserve the information about transformations. This was the idea. The idea uses group invariants. So for a large number of groups, these are called reductive groups. That includes the classical Lie groups, the continuous groups that we care about, and all the finite groups. We have a set of functions that form a basis, and they remain invariant under the transformations dictated by those groups. So for example, if you perform a Euclidean transformation, the distance is preserved. If you do a conformal transformation, the angle is preserved, and so on. And these are in fact bases, meaning that all other invariant functions can be written in terms of these. So the idea was that to create an equivariant network, what we could do is that we could ensure that these invariant bases remain invariant. The value of these QI function, for example, the Euclidean distance, remains invariant as we transform the input. So I'll give you an example for this to make sense. Suppose we're working with a Euclidean group. So what we do is that we take two samples from the domain x and x prime. We encode it using the function f. and we calculate the distances. And then we transform both samples using a transformation. We go from x to xt, x prime goes to x prime t. We again calculate the distances. And we want these distances to be the same in order for this representation to be equivariant. One additional bit that is needed is to make sure that the representation does not collapse. So in self-supervised learning, you have to avoid the problem of collapse. We also have that problem. So if you have something like a reconstruction or a hinge loss that push the point apart to avoid this trivial solution, then that's the objective function you could use to train a self-supervised learning model. So here's showing an example where we use this Euclidean embedding to embed a pendulum. So we have a pendulum, we have two snapshots of the image. And the reason we have two is that because with two snapshots, we can encode both the angle and the angular momentum. So if they're very different, it means that the pendulum is moving fast. So if we just use this training loss recombinant, this is the representation that we get in 3D for 3D embedding. We notice that along one axis, we have what is changing is the angular momentum of the input. And we have along the other two axes, we have the angle. So this loss basically helps us identify these very relevant variables without actually knowing any of these. The transformations that we were applying, they were torques. They were basically just forces that were moving the pendulum faster or slower. If you use a VAE, for example, for the same problem, you don't get a very informed solution. Okay, so that's it. There are more examples of this, applications of this to reinforcement learning or using this to create disentangled representations in the paper, if you find that interesting. Okay, so I'm going to move and talk a little bit about a work in progress on generative modeling using symmetries for generative modeling. The paper on this hopefully is going to come out very soon. The problem is modeling of symmetric densities. So a density is symmetric if when you transform the input, density does not change. The value of the density does not change. So this is important, for example, if you want to learn the distribution of molecules. If you do a rotation of the molecule, you don't really care about that rotation. It shouldn't change the probability of generating that molecule. So you want to learn this distribution of drug molecules up to this set of transformations of rotations and translations, for example. There is another reason you would get a symmetric density, and that's if the object itself is symmetric. So this happens with crystals. Because a crystal is a symmetric object, it automatically is going to make the density be also invariant to its symmetries. So the question is, how do we learn to generate samples from these symmetric densities? You want to learn to generate new crystals, or you want to learn to generate new molecules, but in this case, you don't care about these transformations, and in this case, the object is symmetric. So the usual way to do this is the following. This is a common practice. So what you do is that you start from an invariant latent distribution. So yes. So what's the common practice in generating invariant densities? Is that you start from an invariant latent distribution and you transform that using an equivariant function or equivariant stochastic process. And you end up with samples from this invariant distribution. This is what people do right now. There are some problems with this. is that for some priors, they cannot be invariant to certain transformations. For example, you can't have a prior that's invariant to translation. Think about a prior that's invariant to translation. You can't have a density, right? Or in the case of crystals, actually figuring out what this prior should look like becomes a very challenging task on its own. So, and there is, of course, the computational cost of having equivariant network here. If, for example, you want to be equivariant to 3D rotations, these networks could become expensive, depending on the type of representations that you use. So the idea that we experimented with was to learn to slice the density. That is, instead of learning the entire density, you learn how to produce a slice from the density and then just learn the distribution over that slice. So you can think of this ripple as an invariant density, as a density that's invariant to rotations. And you can create different slices of this ripple and just look at what the density looks like on that slice. This slices correspond to different ways of canonicalizing your input. And the corresponding densities could be very different. So by slicing the density, you could make the corresponding projection on the slice simple or difficult. So, and this is what we are seeing also in our experiments, that it does help learn an invariant density if you learn how to slice that density. Another related problem is that of generating symmetric instances, symmetric data. So in this case, the idea could be explained using this example where you want to create a paper snowflake. You start folding this paper, and then you don't worry that the resulting snowflake will actually be symmetric or not. You just do your cuts and then unfold, and you get something symmetric. So the same way, this space, this unrestricted space in which you do your cuts in crystallography, it's called the asymmetric unit. And so you can do the same thing. You can try to generate parts of the crystal that are asymmetric, and then basically from those try to create the entire crystal. The story is a little bit more complicated because you have to produce symmetry information for each individual atoms in that setting. But the idea is basically this. So one final topic. Okay, I still have time. One final topic that I'll quickly talk about is about symmetries in reinforcement learning. So people know what reinforcement learning is about. You have an agent interacting with an environment. You are in a state, you take an action, you go to the next state, and you have a reward. And your goal is to basically figure out how to act in this environment to maximize your cumulative sum of rewards. There are two types of symmetries in RL. So the first one is called symmetric MDPs. So to show you this idea through an example, suppose you have this Mr. Pac-Man, and this environment has a reflection symmetry, because if I just reflected everything, you still get the same sort of transitions, actions, and everything is going to be correspondingly reflected. This means that you have a symmetric MDP, basically. You have symmetric transitions and symmetric reward, meaning that if you go to the next state and then do a reflection, it's the same as first doing the reflection and then going to the next state using reflected action. So you have a diagram that commutes. You have equivariance here. But there is a second notion of equivariance that comes in because in RL, many aspects of the word are irrelevant to the reward. And you use embeddings basically to get rid of these irrelevant aspects of the word. And as soon as you have an embedding, you have a latent variable, you want the transitions in that latent space to be compatible with transitions in the observation space, meaning that if you go to the embedding space and then there take an action, it should be the same as first taking an action and then going to the latent space. So you have two different diagrams that should commute. So people had looked at these two symmetries separately. What we did was to actually put them together, and we said we want to have a representation that is equivariant to both of these. How do we do that? Again, you can't use equivariant networks, at least not beyond trivial cases, because you have nonlinear transformations. So even in the case of Mr. Pac-Man, you had a symmetric MDP and reflection is a linear transformation, so this part is fine. But the transitions of in the environment where the Mr. Pac-Man is moving to the left or the right, or you have the ghost moving, those are nonlinear transformations in your input space. And so you can't build equivariant networks for those. So the question is, how do we do this? So I'm not going to go through the details, just the general idea is to encode input states and actions both as representations. Basically, you're encoding both of these as matrices. So state becomes a matrix, action becomes a matrix, and the next state is going to be the product of these matrices. And these are special matrices. These are representations. For example, they could be rotation matrices. If we do this, then we are able to actually show that you get a representation that is equivariant to both of these commutative diagrams. We also tried this on a bunch of Atari games in Model Free RL, where we used a special Euclidean group symmetry in the latent space, meaning that the representation that we used where especially Euclidean corresponds to having translation symmetry and rotation symmetry, means that you have, because in Atari games you have these agents that could move around and they can rotate. You could basically, this representation made sense. And we also saw that in terms of results, we're getting results that were competitive at the time. So here the green, you're better than SPR, our baseline that we started from. Also in terms of optimality gap, you're better. Okay, so I'm going to end with an open question. The classical way of using symmetries is by using constraints, meaning that you have equivariant networks. For a lot of application areas that I showed you, we use loss functions, use objectives to incorporate symmetry into our model. There's also a third option of using data to inform the model about symmetries. This is either through data augmentation or through positional encodings. And these positional encodings are often also derived from symmetry. So these are usually the eigenvectors of the Laplacian, which correspond to they are basically equivariant to the symmetries of the domain. So the question that I feel is an important question, and we don't have an answer to, is basically which one to use and why. And maybe this should be qualified under what circumstances, which one of these should be used. With that, thank you. And if there are any questions, I'll be happy to answer. These are the papers that I talked about.